Welcome to Tutorial 5, which is the first of 3 tutorials demonstrating how to load models in OpenGL. The various demos that you can see playing now are relevant throughout this tutorial, so I'll leave them running during this introduction. As always, the tutorial source code is available at programmingcreatively.com, and there's also a direct link in the description. This tutorial demonstrates downloading and setting up CMake, which is a compiler-independent cross-platform software tool that generates build systems build files for programs such as Visual Studio. It also shows you how to build and configure Assimp, which is a 3D model import library that allows you to import into your game or application various file formats that have been exported from a modeling program, such as Blender, which itself is a 3D computer graphics toolset that allows you to create your own 3D models. By designing models in Blender, it means that all of the vertex positions, texture coordinates, normal vectors and various other values are all automatically generated for you when you export the model. In addition to importing models, we're also taking a quick look at the phone lighting technique. 2 of the models that are shown I created myself in Blender for my radio control simulator, namely the Beast helicopter and the Cap 232 fixed wing model plane. The first thing to do is download CMake, as I'm doing here. Make sure you select Add CMake to the system path for all users. Next we need to search for and download Assimp. Once the page is open, click on the latest button and scroll down the page to select the source code zip file, which you'll need to remember to unzip. Once you've done that, open CMake and then follow the steps that I'm showing here, which will generate the various files that you need, including the Visual Studio solution file. After the files have been generated, open the solution, change debug to release, and then select build solution. You can also notice that during the build, the bin folder and the lib folder appear in the build folder. Next, very carefully follow each step as I'm doing here. Notice that CMake created the config.h file and placed it inside the builds include folder, which you need to copy into Assimp's include folder, at which point it'll appear immediately above the config.h.in file. The last 4 steps are to copy the Assimp include folder into your own includes folder, copy the assimp.lib object file into your own libraries folder, copy the .dll dynamic link library that's needed at runtime into your release folder, although the release folder isn't generated until the first time you compile your project, and then finally you need to tell the linker to link with the Assimp library file. One last thing before we start looking at the code and running examples is to download Blender, as I'm doing here, although I'm going to abort at the setup page because I already have it installed. And also, if you find this video interesting, then please remember to click on the like button, and if you have any questions then please don't hesitate to ask in the comments. In contrast to the previous tutorials in this OpenGL Quick Start series, there's actually no new code within the main.cpp file apart from just a single line that declares an instance of our new model class, which is what we'll examine next. First, we declare an instance of the importer class and declare the AI scene and AI node struct instances. Next are the handles for the array and buffer objects, which we'll look at a little later, but by far the most interesting aspect is the code that's within and related to the load model function. Notice the 2 structs, which are the mesh struct and the texture struct, which we declare as the vector variables, mesh list and texture list, which are populated by a sequence of nested for loops. The class starts in the constructor whereby the Assimp importer read file function is called with a 3D model name as the first argument, followed by the optional post-processing flags which tell Assimp how to process the imported data, which we'll look at shortly. After error checking in case the scene object hasn't successfully loaded, the number of model meshes is stored in the numMeshes variable, and then the mesh list vector is resized to the number of meshes. Next, we declare the mesh object, which is later looped through to acquire the vertices, normals, texture coordinates and indices. Also notice there's an indices offset variable, but which isn't actually being used until the next tutorial, model loading part 2. And now finally we get to analyse the 5 for loops which form the heart of accessing your 3D model's data that's been imported and stored within Assimp's data structures. Loop 1. Cycle through the number of meshes, store the current mesh in the AI mesh instance, declare an AI material instance, and store the scene's material data before starting loop 2. Loop 2. Acquire the name of the image file to be loaded, check if the image has already been loaded, and if not, then load the image and store its name and handle in the texture list vector, otherwise just store the existing handle. Loop 3. Cycle through the mesh's vertices and store the vertex positions, normal vectors and texture coordinates in the mesh list vector. Loops 4 and 5. Cycle through the mesh faces, within which cycle through the face indices and also store them in the mesh list vector. And so that's it. As easy as that. For the setBufferData function, there's nothing new to what's already been covered in previous tutorials. Neither is the loadTextureImage function any different apart from using the C++ findLastOf function and the substring function to extract the image file name from the full address which was retrieved by the Assimp import process. I'll now explain about the Vertex shader and Fragment shader and demonstrate a few examples of different Blender models, object files and compiled program runs as we continue. First of all, let's open Blender and simply export the default cube without making any changes to it. To do this, simply select the Export Wavefront Object File option, choose a file location, and then under Geometry, make sure that Triangulate Faces is selected, but deselect everything else. If we open the object file in a text editor such as Notepad++, which is what I'm using, we can see that the data consists of 8 vertices, which are identified by the letter V, and 36 indices, which are identified by the letter F. Because each of the 36 indices corresponds to a single vertex, all 36 individual vertices are being referred to within the object file. Also notice that the program run being demonstrated was compiled without setting any of Assimp's optional post-processing flags. We can also choose to triangulate them by setting Assimp's AI process triangulate flag, instead of triangulating them in Blender, to see how it compares. The result is that we still have 36 indices, but now only 24 vertices instead of also 36 as before. Additionally, if we also set the AI process join identical vertices flag, we then still have 36 indices, but now only 8 vertices instead of 24, which interestingly is the same number of vertices and indices that we used to draw the cube in tutorial 3 by using GL draw elements. Within Blender, let's now select the option to write normals and then look at the object file to see how it compares. The object file now contains 6 normal vectors, which are identified by the letters Vn, which is the minimum data required to then expand upon, and also notice that Assimp has created 24 normal vectors, one for each vertex. You will also now see that the specular lighting effect is working, which was actually already enabled in the Fragment shader, but it wasn't working before because it requires the normal vectors to be imported. Finally, let's now select Blender's Include UVs and Write Materials options, but not before first adding an image to the mesh faces, although this time we'll use a sphere instead of a cube. If we select the View Statistics option and then assign a subdivision surface modifier, we can massively increase the smoothness of the sphere and also see the number of vertices, edges and faces increasing as we do so. To apply an image, first select Viewport Shading, which will make it show once it's applied, then click on Material Properties, then select New, click on the small yellow circle to the right of the base colour, select Image Texture, click Open and then select an image. Once you've done that, you'll see the image applied on the surface of the sphere. Finally, select Blender's Object File Export option as before, but now also check the Include UVs and Write Materials geometry options, and then click Export. The object file now has numerous vertex texture coordinates which are identified by the letters VT. Now let's finish off by looking at the shaders. The Vertex shader contains nothing new apart from the normal matrix, which is the transpose of the inverse of the rotational part of the transformation matrix. When each normal vector is multiplied by the normal matrix, it then becomes correctly rotated as required for the lighting calculations. The Fragment shader is where it gets interesting, and I'm going to replay some of the demos from earlier on in the video. You can notice that I've played around with some of the values and also commented and enabled different lines of code to change the effect. One of the key things to realise is that the various aspects of the lighting calculations can be controlled and applied independently of one another, which allows you to experiment with the ambient, diffuse and specular lighting effects separately. Additionally, you might notice that the varying or transform vertex positions can be set to either override or contribute to the final fragment colour, which results in the changing colour effect being blended with the diffuse result of the sampler image. So then we start by calculating the view direction, which is the line of sight from the camera to the interpolated position of the transform position that is passed in from the Vertex shader. Likewise, the light direction is simply the line of sight between the light position and the interpolated transform vertex position. Notice that the camera position is a uniform variable which is updated during each main loop cycle on the CPU side. The initial colour is acquired from the uniform sampler, which is the image that you chose and loaded within the load model meshes class, which is then used in the ambient and diffuse lighting calculations but isn't used for the specular lighting effect. The ambient result is nothing more than some percentage intensity of the sampler image. The diffuse result adds to this intensity by measuring the angular difference between the light direction and the normal vector by using the dot product, and then for each fragment, the additional intensity of the image becomes greater as the light direction aligns closer to being parallel with the normal vector of the mesh face. This happens because the value for the dot product is between 0 and 1 occurs for parallel vectors, whereas 0 occurs for perpendicular vectors. The specular result is the most complicated calculation. The reflection angle of the light relative to the normal vector is calculated, and then it's the angular difference between the view direction and the reflection direction that is measured, as opposed to between the light direction and the normal vector. The dot product is then used in varying the strength of the light, just like it does for the diffuse effect. However, the resulting dot product is raised to some power, which reduces the specular light strength exponentially as the dot product values become closer to 0, because the multiplication is always of values that are less than 1. Because of the exponentially reducing characteristic of multiplying values together that range from 1 down to 0, a more dot-like specular effect is produced if the power to which the value is raised is greater.